drove off the highway. Her car hit a tree, well, flipped over 3 times, hit a tree, and caught on fire. But she survived it with just a dislocated shoulder. So that kind of got me interested in how do humans interact with technology, and what are some things we need to be looking at in terms of preventing situations like that. So before I get started, I am actually going to show a video that you may or may have not seen that will kind of explain a little bit why this research is relevant. So let's see if it'll load. Let's see. If not, I have. Let's try it one more time.
Are looking at that harrowing footage we first showed you last week. An 84-year-old woman speeding the wrong way down an interstate near Philadelphia. She says she was on her way to the dentist when she caused all that havoc on the highway, driving for several miles on the wrong side of the median. Although no one was seriously injured, she caused 4 accidents. And as Jeremy Hubbard reports, she has also sparked a new debate on whether some seniors should be stopped from driving.
She's barreling down the interstate as if nothing's wrong. An 84-year-old woman behind the wheel of this station wagon, oblivious to the oncoming traffic.
It was traumatic, you know. It was something I never ever thought I'd see.
Tim Fleming pulled out his cell phone camera to record the jaw-dropping sight on I-95 outside Philadelphia Thursday, desperately honking his horn, trying to get her attention.
I saw cars swerving around her, she wouldn't stop, and I yelled at her again. She just waved her arm at me, just like, leave me alone.
Amazingly, no one was seriously hurt, despite the 4 crashes she caused. Her road trip, a reminder of the dangers sometimes associated with older drivers.
This is a critical issue now and will be even more so in 5, 10, 20 years.
Statistics show drivers 65 and older are 16% more likely to cause an accident than younger drivers between ages 25 and 64. So what are the warning signs?
Have there been recent crashes, recent tickets? Has there been a major change in seeing, thinking, or moving? All of those are red flags and should make the person seek formal assessment of their driving skills.
It can be physically harder to drive when you age. ABC's John Berman tested a suit designed by an insurance company to simulate the ailments of older drivers, including a neck brace that limits range of motion. He discovered even putting the car in reverse is tough.
I can't see behind me.
Confusion is the problem for some older drivers. In 2003, an 89-year-old California man mistook his gas pedal for the brakes and plowed into a crowded farmer's market, killing 10, injuring 63 others. As for this confused driver, her family says they've now taken away the keys and the car, and they're keeping a close eye on her.
All right, so you can kind of see this, you might say, is an extreme example, but it's something that's happened, right? And so in Human Factors, our goal is to do as best as we can to design systems to prevent things like this from happening. So the overall goal of this objective of my research at a very high level is really to ensure the safety of the older adult population. And some people might say, well, why are you focusing on that? As I talked about my interest in human factors coming from my experiences with my sister, my interest in older adults kind of came from my experiences with my parents, both of my parents who are in this age group, and kind of some of the things that they struggle with, some of the questions that they ask, some of the things that they confuse, and just going along life and kind of thinking about, I wonder why do they think about things this way? Why does this confuse them? So on and so forth. But if we step back a little bit, in many high-risk, data-rich, complex environments such as driving, military operations, space, aviation, over a number of years, multiple decades, a lot of these domains have been saturated heavily with visual data. And you can kind of see it, it's very evident. Many of you all are familiar with these domains. But what this visual data overload has done has caused associated performance breakdowns, such as participants feeling overwhelmed by the visual clutter or missing signals that they should not. And so one way in which people have tried to overcome this issue is by introducing these multimodal displays. And multimodal displays are simply displays that present information not only visually, but through the sense of hearing and through touch. So for example, adding lights to sound to a vibration. And you can think about this vibration of your cell phone as a tactile alert. You can think about the tone of a text message as an auditory alert, and then visual information you're faced with all the time. So extensive research has investigated these designs and they have been shown very effective, for example, in reducing visual data overload in the sense that you're presenting more information to hearing and touch, offloading the visual channel. It's also been shown to improve multitasking, so people are able to perform more than one task at a time because you're distributing the information. And also we can do a better job about capturing people's attention and directing it to where we're supposed to. The kind of implementation of these designs was suggested by early research on time sharing, which led to the development of this multiple resource theory. And simply this theory states that we have separate sensory channels for which information can be processed, and thus we avoid resource competition between modalities. But even with the design and introduction of these displays, we are still possibly getting ourselves into a condition or a situation where a person might be faced with more than one concurrent source of information, right? And this information might differ from one another. So let's just take a doctor, for example, who's performing some kind of surgery. Well, let's say he's performing a laparoscopic surgery. Most of his information will be visual, but he also needs to be attentive to listen for auditory signals, for example, about vital organs of the patient, right? And so you might say, well, doctors are trained in a sense to be attentive to that. That's absolutely right. But let's think about another condition. Imagine that you have a car that was built in 2015 and you're driving down the highway, you get a visual alert from a GPS system, while at the same time you get an auditory alert from a lane departure warning system, and at the exact same time you get a collision warning alert through your steering wheel giving you some kind of vibration pulse, right? If you can imagine yourself in this situation, what is the likelihood that anyone, not just in the 65 and older category, but anyone can really handle this? And so this is really the foundation and the basis. The question that we're trying to answer in this research is can someone handle this? And this is critical because we can find ourselves in a situation of this nature, right? You look at aviation, pilots are presented with multiple sources of information, sometimes conflicting, sometimes related to one another. So this is critical. But most studies in the past have only evaluated the need. So because we can possibly get ourselves into a situation where someone is faced with 3 different signals and 3 different sensory channels that relate to 3 different events, there really is a need to understand how do people handle this. Especially because in the literature, people have tested combinations mainly of only 2 modalities at a time. So what does that mean? Well, they run many experiments where they were testing visual and hearing only, visual and touch, or sound and touch. So, have someone perform an ongoing task and you have some type of information presented visually, some type of information presented auditorily, and you can kind of see the benefits that I talked about earlier. There have been very, very, very few studies who have employed the use of all 3 modalities, and most of them have used what we call redundant cues. So that means that the cues were referring to the same event or presenting the same information. A very popular or common example of a redundant cue is if you're driving down the highway and it's time for you to get gas, you'll maybe get a light. You'll get a visual indication, but also an auditory indication. So if you miss the light, you get the sound, or if you miss the sound, you hopefully see the light. That's what we call redundancy. But here we're interested in what happens when cues are not redundant, kind of the driving example I gave. There's been one particular study that looked at this case, and what they found is that when you present 2 stimuli at once, and the majority of the cues are visual, participate in more complex tasks, for example, driving. But then the multimodal literature that's using vision, hearing, and touch has not really investigated how well older adults can kind of benefit from these displays. When they do so in more simple human-computer tasks. For example, dragging and dropping a mouse, or dragging and dropping a file from a desktop computer and being provided with some kind of multi-sensory feedback. But there's really a reason other than my interest in aging why we can't really ignore aging, and that is primarily due to the fact that within the next 14 years, they're expecting 72 million older adults in the U.S. So that's somewhere around 21% of the U.S. population containing people in this age group. But not only will there be more older adults, but kind of as a direct result, there'll be more of them working and more of them driving. And so this is kind of where this is coming into play. But just kind of at a higher level, if we want to think about why do we need to pay attention to this, so it's really to make sure that we're supporting them, right? And that as they get older, they're still able to do things that they were once able to do. So one thing, aging in place, basically not paying attention to a person's education level, physical ability, income, not letting any of that get in the way of them still being able to function in society. It also gives them the chance to retire later. Some older adults aren't ready to retire, and they should have. Some people want to work until they're 80 and 90, and if they should have the choice to do so. So the more we can design for that, the more we can allow, and then increase social participation. So. From what I understand, a lot of older adults kind of get nervous when you start talking about taking away driver's license, and it makes sense, right? Most of us don't want to be dependent on someone if we don't have to. And so this is kind of why this research is important. So with that being said, my research, or my thesis research, has been broken down into 3 main phases, and I'll kind of walk through each. But the first one was to develop a cross-modal matching task. I'll talk a little bit about what that is. The second point is to kind of determine the case that I talked about, the combined VA and T. And when I say VA and T, that's visual, auditory, and tactile, both in the absence of an ongoing task and in the presence of an ongoing task. And then finally, to kind of start thinking about what kind of countermeasures can we take to avoid people missing signals when there should not. So the first part was to develop and compare cross-modal matching techniques. I'll go into a very good example about what that means, but there were 2 goals here. The first one was to determine whether different techniques result in equal levels of within subject variability, and then to identify the one technique that will be used in future studies. So let's just go at this. If we wanted to consider a case where a study was comparing the response time to visual, auditory, and tactile cues in isolation, and let's just say that they found that participants responded faster to tactile cues as opposed to the first 2. If this study hasn't conducted or performed cross-modal matching, then we can be sure if those results are due to the differences in sensory channels, for example, stimulation rate or conduction velocity, or if it is simply that the tactile stimulation intensity was higher than that of the other 2. And because of that, this is why cross-modal matching is needed. So it really refers to this process of an observer or a participant in an experiment matching the perceived intensities of one modality to the other. So if you can imagine matching the brightness of a light to the loudness of a sound, or the loudness of a sound to the strength or the gain of a vibration sensation. And we do expect that if I ask 2 different people to perform this, that there will be differences between people. But if I'm asked to repeat the same match over and over, there should be some level of consistency. And that's what I mean when I talk about within subject variability. We did a survey of the literature over the past 20 years to kind of get a sense of all of these studies reporting these benefits of using hearing, using touch. And surprisingly, less than 5% of all multimodal studies that are specifically in the human factors and ergonomics literature have reported or report performing this stage, right, at this step. And what you can see here, not only are there few of them reported, but you can kind of see the variability in the matching tasks that are performed. So these are basically 11 studies that have reported them, and you can kind of see no 2 of them, except the ones that these little lines means that the information was unavailable, no 2 of these use the exact same method. And so that maybe presents an issue if people are using different methods to try to come to some conclusions. But what's more important is there's much more information that's unavailable. So for example, a study might say, well, we perform cross-modal matching and that's it, but not really giving any details for any other researchers to kind of pick up and implement in their studies. There was one other thing. Oh, there also have been, yeah.
2 slides ago, you showed this bar graph.
Yes, right here.
So is this a specific study?
No, this is just a prototypical scenario, yes. No, not at all. Another thing here is there have been few studies who've even made any kind of mention of psychophysics. So some may say, well, we didn't perform cross-modal matching, but we at least tried to use threshold values, okay? That's at least better than not reporting anything at all. So what we did was came up with a technique that would use a variety of things. The first thing was alternating stimuli. So what that means is you present a participant with one intensity and ask them to adjust the intensity of another stimulus to match that of the first. Okay, and this has been done in both directions. So it's important to know whether the order of presentation makes a difference in terms of repeated matches. We also use these methods of adjustments in which participants were in full control of the spectrum. So we did not, in a sense, force any kind of results or limit participants in a sense. We allowed them to have the full range of values. Okay, and then we also use these three techniques, which all three of these have been used in those previous studies. So in one case, there was a sliding scale and a mouse technique where participants simply used a mouse and a scale to drag and drop or to increase. So this is kind of the breakdown of the experimental design. A total of 18 participants, 3 matching techniques, 3 reference Q intensities. So what that means here is what we had experimentally set for them was set at 20, 50, and 80. So it's kind of representative of low, medium, and high intensity values, respectively. And then the match type. So this is kind of where the order of presentation comes into play. So in one case, we presented, for example, the V and A. And then in the next one, it was the A and V, like I say, to see if the order made a difference. The dependent measure was simply the intensity value that they selected. And then they repeated the matchings 3 times per each pair. And then there was debriefing sessions for them to kind of provide us with comments. So since we were interested in this in the within subject variability or the within subject consistency, so consistency is positive, variability can be negative. What we did was looked at or made use of these residual values. So if you can imagine a case where a person was presented with a light at 50% its brightness and asked to match sound, each time they might have given 3 different values. So one time they might have given 35% of the auditory cue, 45%, the next time 50. What we did was simply average those and then subtracted each value from the average to kind of get residuals, which would have given us how far off the matches were from one another. So just kind of a few things we noted here. This is what we see when we plot the average residuals as a function of the match type, the reference value, and for each technique. So one of the first things we see here is the green line is always the keyboard arrows. The red line is the sliding scale and mouse. And what we see is that in most cases, the keyboard arrows led to the lowest residual values, meaning the lowest within subject variability, where the sliding scale and mouse generally led to the highest. And we also kind of see that as you increase the reference intensity, residuals are increasing, right? Another thing that we noted was generally when the tactile cue was the one that was the reference, the match was the match for that was higher, and we'll kind of talk about that in a second. So you can see here, this is what they were presented with. They were asked to match to. The same thing here. Whenever T was there, it generally led to highest variability. So just to kind of summarize what happened, we did in this small experiment find that different techniques do produce different results. So that kind of raises concerns about matching tasks who have not used the same. We're not saying that everyone necessarily should be using identical ones, but something that's a little bit closer than just kind of all over the place. So the visual sliding scale is not advised. This is something that we had not known, techniques that people have been using. One thing we got from the debriefing comments was that participants, in a sense, were more focused on trying to be more precise in sliding that scale than they were focused on the actual sensation produced by the stimuli, okay? So because of this, and it seems a little strange, but the keyboard arrows actually tended to be the most reliable. And that's because what we think is that that's the one technique that allows people to make kind of incremental steps towards the appropriate value, as opposed to overestimating and underestimating in either directions with the other two tasks, right? So in one, you may slide the scale too far, where in the rotary knob, you may make an adjustment entirely too much and therefore need to correct more in either directions. The order of stimulus does make a difference, which was something that we found. And then this high variability with a higher reference intensities possibly suggest that we're getting to a point of some thresholds where it's more difficult for people to detect those higher differences between higher intensity values. So, like I said, this was really needed to where we can, since we are using older adults who have varying hearing, sound, and touch decrements, we needed this in order to allow them to use this before the other experiments. So the second stage was to use that keyboard arrow techniques and really determine the extent, like I said, to which people can detect and process these non-redundant cues. There were two really main goals. The first one was to kind of compare the difference between younger and older adults. And the second was to compare performance when people do this task in the absence and the presence of an ongoing task. And for this, we use driving, and we'll talk about that. But in the first experiment, this is the absence of an ongoing task. We had a total of 36 participants, 12 of which were students, 24 of which were older adults. And the older adults were broken up into two categories, some that are still working and some that have been retired for an average around 8 or 9 years. The design we used was the 3 age groups, so 3 by 7 full factorial. And then 7 different cue combinations. So even though we were very interested in this, we needed these in order to establish a baseline. So if we had just started with VAT, we wouldn't have been able to know if people can reliably detect multiple things outside of that case. Okay, and then we simply measure response time and accuracy of these cues. So this is kind of some demographic factors about each participant. So the average age for the younger adults was around 23. The 2 older adults was around 68. And both of them had worked for about 34 years. The retired group, like I said, around 8 years. The females, and then in order to make sure it was fair, we performed a variety of divided attention assessments and cognitive assessments to make sure we were excluding those with maybe extreme cases. All right, so for the first experiment, this was the generic task. It was very similar to what you saw in the matching task, where the auditory cues were through the headphones, the visual cue was the light bulb, and then the tactile cue was located on the back of participants. And what they were simply asked to do, they were presented with a total of 196 cues that were presented on average every 6 seconds. And what they simply were asked to do was press a space bar whenever they heard, saw, or felt anything, or any combinations, and then verbalize to us which ones they saw, felt, or heard. So in any case, a person might have been presented with just a light and a sound, a light and vibration, or all three. And they simply used the same response and then told us what they saw, felt, or heard. So there were some possible things that could have happened. In the example, for example, if someone was presented with a light and a sound, they could have given a correct response, a light and a sound, or they could have missed one or both. So they could have said light or sound, or responded nothing at all. They could have also substituted. So instead of saying light and sound, they said light and vibration, or vibration and sound, or they could have added something. So instead of saying light and sound, they said light, sound, and vibration. So if we look at what happened with the response times, we can see that the response times for both older adult groups were significantly higher than that of the younger adult group. Okay. And then if we look at overall what happened for the response time in each combined case, we see that generally that participants responded faster to combined stimulus than they did in the single stimuli, right? And so we'll talk about why that's the case. In terms of the accuracy, so this is them reporting to us what they saw, felt, or heard. The accuracy between the younger and the older retired group was the most significant. And then let's just walk through a little bit what this looks like. So in terms of the correct percentages, so almost 100% for the younger adults and somewhere a little bit maybe 95% for the older retired adults. The most common error was a miss, followed by an add, and we'll talk about what this means. And just remember, this is in the absence of an ongoing task. So this is where it becomes very interesting. So this is plotting for each age group the response accuracy. So if I plot this for just the younger adults, we see that for the most part, they're pretty good about it. This is why it averages to that 99%. If I show this for the older working adults, we see that in the single cases where there was just light, sound, or vibration, they're pretty good. But then performance starts to suffer a little bit when we get to the combined cases. And then when we look at it for the older retired adults, for these combined cases, it's even more, it's dropping off even more. And so there were two things we noted here. For both older adult groups, when they were presented with the light, sound, and vibration, they tend to not report the vibration. And then something else that was interesting we found was whenever the older adults, this is particular to the older adults, whenever they were presented with a sound and a vibration, they tend to falsely report that a light was there. So they get sound and vibration and they say that was light, sound, and vibration. So does that make sense? Okay, so just kind of wrapping everything up, in terms of age, both older adult groups, regardless of working or retired, did show longer response time and higher error rates. And I think which makes sense. We talk about slowing processing over time. And then for the Q combinations, this is something that had been shown in the literature, is that bi and trimodal, so bi is 2 Qs and tri is 3 Q modalities, the response to those are quicker than singles. And one proposed explanation for this is that the brain allocates more attention to events that activate more sensory receptors at once. Okay? And this was the case for each age group. But what was more troublesome is that whenever older adults were presented with VA and T, they often missed the T. And when they were presented with just an A and a T, they often added a V. And we can think about both of these being a dangerous case. If we put it in terms of the driving example I gave earlier, if I miss anything, if I miss even just one, that could be the difference between an accident or not an accident. But then if I also think that I saw something and I didn't, and I respond in a way that I'm not supposed to, that could also lead to some trouble. It's kind of the same thing when someone has a cell phone and they're kind of feeling around to see if it's vibrating. They think they felt something and they really didn't. It's along those same lines. So with this, we use that same design to put it in the context of driving for a number of reasons. So not only I talked about some of the stats about the older adults, but they're also projecting that 25% of all fatal accidents that older adults will contribute to that percentage just in the next same time period, 14 years. But multimodal technology is more likely to be found on newer and more expensive vehicles that can be afforded by an older adult population. So the participants were the same. So this was to be able to directly compare performance, and then the exact same experimental design. So we used a medium fidelity desktop driving simulator called STI SimDrive, where there is a associated steering wheel and foot pedals for participants to drive. And the setup looked like this. So very similar to both the matching task and experiment 1, where auditory cue is the same, visual cue is the same, tactile cue is the same, but the task was slightly different. So instead of just being instructed to press a space bar and kind of verbalize the responses, they now needed to press a button that was on the steering wheel and still verbalize the responses. They were asked to drive at 50 miles an hour and kind of stay within the center of the lane, but they were still presented with those total 196 cues altogether. And so we'll get into the performance measures later, but let's do a direct comparison. So the detection task was still accuracy and response time and accuracy. So if we look at that, this is only for the younger adult group, and right now we're still in the process of running this. Within the next week we'll be finished, but this is only 6 of the 12 that are in that group. But we can kind of see so far for just them, the response time while driving, which is highlighted in red, was about 1.5 times higher than when there was no ongoing task. Okay, and then if we look at exactly, I think I must be missing something. This is out of place, but for the older retired adults, we have 10 out of the 12, and we can kind of see that their response times are doing the same thing, right? So maybe this is closer to 1.3 or 1.4 times as higher. Nonetheless, higher when they're driving than when they're not driving. But But if we look at the accuracy, we see that there's been a slight decrease, not as much as what we thought, but a slight decrease in the detection. This is only for older adults, so down from 95 to somewhere around 93. But the two most, the errors that occurred most often were still in the miss and the add. And then if we kind of look exactly at what that looks like, we can kind of see that's denoted by the red. This is the accuracy. The accuracy that it's following the same general trend where they're having more difficulty with the combined cues than they are with the single cues. And then in terms of, that's the early experiment, right? Okay.
And another question is, so what are these things, so what does VAT translate to in an actual driving scenario?
Yes, so this is just light, sound, and vibration that could represent anything. But for this research, these cues didn't have any associated meanings because we were really interested in if people could perceive it. So they weren't asked to give any kind of any response or like make sense of the cues. It was just simply to find out if they can perceive them, just as a first step. Okay?
But it's also possible that when you're actually driving, some of these cues are redundant.
Yes.
So how are you taking that into consideration?
So that is just a case that we're not considering. For the purposes of this study, we know just from the literature that redundancy does, in a sense, produce faster responses and more accurate responses. And it's possible that in vehicles we could see a combination of redundancy and non-redundancy, but this is only focused on redundancy.
And would you see a similar improvement with older drivers?
In terms of redundancy, yes. In terms of accuracy, yes. In terms of response time, about the same. Okay?
And just one more question.
Yeah.
So in the experiment that you had,
Yes.
it seemed as though people were driving in the simulator. There were no other vehicles.
Yes, so I'm glad, that's one thing I forgot about. So yes, so right now the background is just a beach scene, but it really was a highway scenario where there were no other cars, no other sounds, no other vibration to kind of rule out the fact, to kind of not introduce any distraction. So one of the next steps could be to get a little bit closer. So these experiments are really establishing a baseline for people being able to do it. But if we find that they can't do it when there's nothing around, then we can only imagine what that would look like if there were a lot of other things around. Okay. So, and in terms of the driving performance, this is just standard. A lot of this is standard in driving literature. So simply, how fast are the people driving? How fast are they moving from side to side in the lane? And then how accurate how much can they control the steering wheel to stay kind of in the center of the lane? And so right now, again, this is only with a little bit more than half of our participants being run. We see the main differences in terms of average deviation in lane position. So what does this mean? Well, what we did was calculated these measures 5 seconds after the cue was presented. And so what we see so far is that it appears that events that contain a visual cue seem to afford people the opportunity to drift out of the lane more than the other two. Okay. And then just in summary, so the longer response times was found for both groups, and this is compared to the first experiment. Somewhere around 3.5, so 1.5 for the younger, somewhere around 1.3 for the older. Okay, and slightly higher error rates. So this was something that was a little surprising to us because we thought that if a person is asked to engage in an ongoing visual manual task as opposed to detecting cues alone, that performance will drop. But it's kind of getting at the question that he asked, basically is that even though they are engaged in an ongoing task, there is still no other distraction. So people, in a sense, are using the same strategies that they use to focus when driving for this. Now, if we went a little bit further and kind of introduced more cars, more sound, more vibrations, we may see some differences. But again, I must emphasize the fact that even if anyone misses just one signal, that is not a good situation at all. And so we're seeing these 93%, which is 7% errors, but 7% is still significant and it can still contribute to these statistics that we're talking about in terms of fatal accidents. Greatest deviation in terms of when a visual cue was present for the lane position. And this, in a sense, makes sense. We didn't collect any eye tracking data, which would have helped us be able to understand or kind of see where participants were looking, but it's possible that even when they get a visual signal, they take their eyes from the road for a second, which causes them to drift out of the lane a little bit. And so the expectations for the expectations for the rest of the experiment, once we're done with everything, it's very possible that we find that even though the detection task is not suffering for older adults, it's possible that they're struggling a little bit more with the driving task. So there was an incentive for them to divide their attention between the detection task and the driving task. And like I say, since we're not seeing these kind of negative results in the detection task, it's possible that they'll surface in the driving task. Okay. And then just the final phase of this research is, again, everything so far has been perceptual. So really trying to see if people can can notice these things to begin with. So the last phase is to kind of start thinking about some countermeasures for helping people helping people notice things that they're supposed to. So some people might say, well, why try to overload people? Well, it's not overloading in a sense, right? We see that the younger adults are able to do this. So what we're trying to do is bridge that gap between the younger and the older to still give them the same capability of the younger adults. So some simple things that we're thinking about doing, this experiment will be tested in that same driving context, and we'll be focused on the older adults since their performance is significantly worse. And then just some minor adjustments. So one idea might be to present cues with a slight time delay. And we're not talking about minutes apart, we're talking about milliseconds apart. So for example, if they fail to notice the tactile cue, one possibility would be to present the light and the sound together, and the tactile cue may be of 50 to 200 milliseconds afterwards, right? Another thing might be is to increase the duration of the signal. So maybe present the light and the sound for 1 second and the vibration for 2 seconds, right? Another thing could be a salience adjustment. So what do we mean by that? Well, they've engaged in the crossmodal matching task to be able to equate these the level of stimulus. But one thing might be to increase the salience of the tactile cue to make sure that it's somehow encoding in the memory longer. Right? So just some simple things we can do that even automotive companies can kind of think about when they're designing displays to kind of get right, what's the duration of cues, what should be presented first, what type of information should be presented in which modality. So right now they're doing lane departure in both visual, these lights in the side mirrors. There's also lane departure in the seats. Sometimes the seat vibrates to let them know that there's someone here, so you need to move over, or there's someone here, so you need to go over the other way. So just kind of a better understanding of how to properly design these displays. And so this is the final step, which will take place within the next week. So that is the wrap up for the current dissertation. And then these last few slides are just going to talk about some future research that I'm interested in. And it's broken down. It's in a sense, it's an extension of what I've already done, and it's moving into some new areas. So the first one is this needs assessments of older adults. The second one is automated vehicles. And then the third one is kind of assistive technologies and devices. So if we look at kind of this needs assessment, so one thing we found in this literature is that there's been a lot of reports about really quantifying negative performance of older adults, but not really getting their opinions. So what does that mean? Well, if someone was going to design a computer for you or some shoes or, I don't know, a house, would you want them to guess what you want, or would you want to be able to tell them exactly what you want? And so this is kind of one critical part that's been missed, is kind of really sitting down, talking to them about what has their experience has been, what are some things they like to use, what are some things they like to see, what are some self-identified things that they think can help them. So some ways of doing this are kind of some ethnography, field studies, some direct observations, surveys, interviews, focus groups. And there is a center here on campus for this, a Center for Aging and the Life Course. And then kind of once we have a better understanding of these things, kind of educate them on their abilities. Because I think a lot of the time people are too quick to say, oh, well, I'm older, so I don't do this as well. But if we can show them data on how well they perform, maybe we can kind of empower them and make them feel a little bit better. So that's one thing. Another thing is, this is not going to stop, but right now we're talking about moving more and more into this autonomous future. And so the human factors people are really jumping on this. So if we kind of look at how cars have evolved over time, we kind of see there's this gap. And I wish I could put a year on this future, but I can't. But nonetheless, we're going to move more toward autonomy. And so what we have to think about as human factors experts is kind of for older adults, what kind of are the next best systems that will help them? So right now there are some cars that are that can perform lane keeping, but what are some things that will benefit them? What's the next best thing? Should it be customized steering? Should it be some cars are customized parking? But what really will benefit them? And this will kind of get us into some exploration of new models about how do you keep the human in the loop, some things that have been revisited for over 30 years now. So it's kind of a person is driving and, let's say we are to this autonomous future. Well, what are some ways that we can monitor a person? So it's not so much the person monitoring the machine, but how does the machine monitor the person to kind of figure out when do I wake them up, when do I alert them, when do I warn them in cases that they need to take over, things of that nature. Okay. And then the final thing, kind of going along this same idea of assistive technology and devices. So we see from this experiment and from the literature in general is that there is a difficulty in dividing attention. And so how can we design these multimodal, still, vision, hearing, and touch? How can we design displays that really support divided attention to older adults? So what does that mean? Well, adaptive displays are displays that adjust the amount, the timing, the frequency, the location, duration, all of these parameters of signals and in response to poor performance or performance deterioration. So I don't know, let's just say we can use eye tracking to see that a person is looking in one area of the highway when they should be looking over here. So how can we create some kind of adaptive alerting system to kind of monitor again where the participant is mentally and kind of direct their attention? This is what adaptive displays is about. And then kind of a national robotics initiative. So there are some people down at, for example, Georgia Tech who are working in kind of assistive technologies and robotics for older adults. So those who are, I mentioned this agent in place, so kind of supporting that. Those who are maybe 80 and 90, who are living alone, maybe they don't have a spouse, maybe they are limited mobility. So how can we design robotic devices that can support varying needs of older adults? How much would they want to use them? How much would they rely on them? And for what kind of things? And then can we somehow use multimodal displays to kind of support the interaction between humans and robotics? For example, if I'm forming an intention and I want the robot to understand what I do, can we use displays to help older adults be able to correctly explain their intention to where the robot can do exactly what it is they need to do? So that is that. Some funding sources for this work is primarily in healthcare, so the National Institute on Aging and the American Federation for Aging Research. And then the last thing I have here is just some courses that I'd be interested in teaching. So I had said already that all of my background has been in industrial engineering. So there are courses, primarily in human factors, but even outside of that I'd be interested in teaching. And then at the graduate level, of course, and then possibly developing or picking up a course that hadn't been taught in years that kind of talks about processing, perception and cognition, kind of some design principles, some things that we need to know about in terms of human perception and cognition. With that being said, I want to thank the university, the department, just everyone that's been supported. I've had a great time here. My advisor, my Think Lab members, and the help from the Geriatric Center who really helped us be able to identify healthy participants, and then the agencies that have funded me through my PhD. So at that time, I think I will take any questions now. Yes.
With the driving situation, we perceive the peptides stimuli from our hand.
Yes.
The hand might be more sensitive
Then back, correct. So, so actually, these are two things. There are some vehicles that are presented on the back. So actually, in the seat pan or the back of the seat, kind of a status or command situation. So that's kind of what I was talking about, where if you need to move to the left, you'll get kind of a pulsing on the left leg telling you to move to the left, or the right leg, or so on and so forth. So cars have really made it to where they are presenting signals both in the steering wheel and on the back. I guess for simplicity, it was easier for us to implement it on the back than it was on a steering wheel, but that also could be maybe a next stage. Okay. Yeah.
Quick question. You talked a lot about the multimodal display.
Yes.
But it looked like in your second experiment, you also had a multimodal response.
Oh, so I don't think so because so just by the.
Didn't you actually have speech plus or some kind of a
Yes,
response?
but those responses were only being captured for accuracy. We weren't analyzing any if the response type has an effect on performance. But that's maybe something we can look into.
So I was just interested if there was any difference in
Yeah.
related to the modality of response.
So I was just going to ask, so in terms of what auto companies do today,
Yes.
do they actually use some kind of research like you're doing to decide, whether to use a vibration technique or a visual cue?
Yes.
How do they decide? And do you plan to work with it?
Yes, absolutely. So from my understanding, and this is just being in close to Detroit where there's a lot of this work going on, these companies have their own human factors groups where they try to do as best as they can, right? But the participants, and I hope I'm not the participants in these experiments tend to be employees of the company. And so that's good. I mean, there's an advantage there, but then if we want to kind of extrapolate these findings to a larger population, then I think it's critical that we kind of consider variety. And that's kind of what we got at that was the reason for getting two older dog groups, to kind of show, even though it's the same age group, the same type of job. One thing I didn't say is that we tried to get people who had been doing the same kind of job. So someone who wasn't maybe working in fast food as opposed to someone who was a business manager, we tried to get people who have been working in similar domains. Yeah, so, but if I have the opportunity to, I would love to kind of work with them and kind of see what are some things that they need help with, better understand what are some things that they're doing, and maybe be able to enrich it in some way. Yeah.
Do you have any idea about which one will be the interface that will be actually providing information to your feedback system about what is the age of the person that is riding the car, or if they are particularly nervous, or having some sort of problem with anxiety,
Yeah.
or if they kind of visual signals that you're providing is just overloading them?
So maybe I don't understand the question. Can you just?
So the idea is how do you plan to make this? So basically, what you're creating is some sort of passive, basically feedback to the driver.
Yes.
Once you know how the driver is and basically which ones are the limitation of that person.
Yes.
But what happens when somebody shares the car with somebody else, like me with my grandpa, for example, and we have completely different needs? Have you considered how you're going to implement some sort of active and adaptable your system?
Yes. Okay. So that kind of gets into the adaptive displays that I was talking about, and that's kind of a general sense. So how do we develop adaptive displays in general that can kind of gauge where the person is looking, where the person's mind is, and then adjust displays based on that. So adaptable is in a sense, you can think of it as customizable. One solution might be, and this may be far down the line, where if you are better able to respond to tactile vibrations, when I talked about the next automated system, one thing could be using a thumbprint for vehicles, where when you get in, you can set intensities, you can set modalities, have the option of what presents what and how. So you can do that for you, and then someone else can come behind you. Your grandfather drives in your same car and can program that, but in a different way, to where it's kind of suiting both needs.